All right. Today is lecture 25. We're going to be continuing our discussion of standard model particle physics. We're going to be talking about the spectrum, the Higgs sector, and strong interactions. As usual, if there are any questions, do ask. I'll start by a review of the standard model as we described last time. So, standard model of particle physics is a particular quantum field theory that is supposed to describe the weak nuclear force, strong nuclear force, and electromagnetism. Not supposed to, it does describe it. Not gravity. It's a non-abelian gauge theory coupled to matter. It's a 3+1 dimensional theory. So that's what we've been building towards all this course. The gauge group is SU3C for color, SU2 left for L for left-handed, U1Y for Y for hypercharge. The matter fields are Majorana fermions. They're fermions, right? And a complex scalar field, right? We have left-handed, right-handed. Okay, so what are the masses of the fermions? Today we'll see. None of them will have any masses. Why?
They acquired it via spontaneous.
What?
They acquired it via spontaneous.
But why do we not write mass terms? It's a gauge theory. Yeah, gauge forbids it. So the only field that we're gonna have started with mass is the Higgs, and the mass of Higgs, or the action of the Higgs will decide the mass of all fermions. So very important Chekhov standard model is all these relations between the masses of these particles that are implied by a few parameters that are related to Higgs. One thing to have in mind is that you already, so I'll come back to this and talk about it. The whole course, we've been pretending mass term is fine, but you learned that mass term is relevant. Right? So if mass term is relevant, it means they keep growing in the infrared. Right? Mass is not protected under quantum loops. It will grow. That's not good. We'll come back to this. That's one of the issues of the standard model of particle physics. And that we don't have an issue except for the fact that we have to include the mass term for the Higgs. All right. It's a fine-tuning issue. All right, spinner is in 3+1 dimensions. A Dirac spinner is a 4-component spinner that we introduced this notation for. It transforms this way under Lorentz transformation. We discussed in the chiral basis. This is how you write the generators of the Poincare transformations. Lorentz transformations. Here are the boost, and here are the rotations, right? These are reducible representations. Hence, you can view the up and bottom two components as separate degrees of freedom, chiral degrees of freedom. Good. So the two component fermions, you could use the projections to the PLP right to think of them as chiral left movers, right, left-handed, right-handed. And the point here is that if psi tilde L is left-handed, if psi L is left-handed, epsilon psi L star is right-handed, right? So in Majorana spinners, we could invent the right-handed part of psi so that this way, and we could complete it. It's a choice of basis. Majorana fermions are their own anti-particles. We could use Majorana or wild fermions as a choice of convention to present our theory. We're going to be, in this course, we're going to be talking about Majorana notation. That's the notation I picked. Now, can anyone tell me what is the advantage of them? What could be an advantage of Majorana? This is all about the fact that it's its own antiparticle. So what are we doing? What's special about Majorana?
Once you solve the two upstairs then the answer is
Yeah, but in chiral wild fermions, there is nothing else to solve, right? It's just one side. So what is nice about it is charge transformations. Somebody said parity last time. Parity is the wrong answer. Charge transformations. So recall from QFT1 what the charge transformation is. The origin of charge transformation is the Clifford algebra, Dirac algebra, right? Dirac algebra is this. Now, if you found Dirac matrices, gamma mu that solve this, gamma mu, if you take the transpose of them, they can continue to solve this equation, right? So the transpose of gamma matrices are also legitimate, result in legitimate representations. This is the origin of the charge that we discussed. So there is a charge operator that sends a fermion to its, what do we call this? Antiparticle, which is, like its action in the Hilbert space is CC dagger. This is a Z2 symmetry, right? It's a discrete symmetry, it's a Z2. And then we saw that in QFT1 that what it does when you expand the fermion, Dirac fermion in terms of the BS and DS, right? 4 degrees of freedom particle, it swaps the fermion, particle antiparticle without acting on the K modes, right? Whereas parity adds the minus sign to the K modes. So the action of this on the Dirac fermions and the basis that we've discussed is minus I gamma, not gamma 2, not the basis. It's the action of it this way, right? Psi transpose. This is what it does to the fermion. Now, a Majorana fermion is its own antiparticle. What does it mean? It means that under charge transformation, it's left unchanged. It's an eigen operator of the charge transformation. Now, let's go back to the philosophy of what a particle is, right? A particle is a near-reducible representation of the Poincare group, right? CPT was a discrete part of the story. It was not the full, like when we talked about Poincare group, what we meant was the connected piece of it, SO3, 1 plus direct sums with R3, 1. This is the discrete part, right? So what we're doing by picking our particles to be fermions, fermions to be Majoranas, we are diagonalizing in the charge basis as well, right? We're picking the eigen operators of that, and physically it just means that the particle is its own antiparticle. Good? It's just a review of the last time I asked the question last time, but now I explained. If you have any questions, do ask. The gauge sector. So we talked about the gauge sector. It's a renormalizable interacting 4D QFD. Their gauge group is SU3. There are 8 gauge vector. There's 8 gauge vector fields, gauge bosons. 8 because that's the dimensionality of the Lie algebra of SU3. SU2 left times U1y hypercharge is the theory of electroweak. There are 3 gauge bosons for SU2, and then there's 1 B mu for U1. Today we're going to see that this U1 is not a U1 of electromagnets. So this SU2 left times U1y is spontaneously broken to U1 electromagnetism. This one particle, this one spin 1 particle is not the photon. The photon is something else. So we're going to see that today. These are gluons. These are the W bosons. Well, actually, the term W bosons is also reserved for something else. But anyway, this is B mu. Good. And then the fermions come in 3 generations. Hypercharge is not electric charge. That's very important. Good. So we're going to see today what is electric charge, electromagnetic charge in terms of the hypercharge. Not just the hypercharge. It has to be related to SU2 as well. All right. So the leptons, I repeat the definition. These are spin half particles with no color charge. These are fundamental particles with no color charge. They do not participate in strong interactions. They come in 3 generations, right? And there's electron, muon, tau, and their corresponding neutrinos. Why do I present it this way? Because electron neutrino the left-handed part of them, well, electron, neutrino, a neutrino is itself only left-handed. They sit in a SU2 doublet, right? The left-handed side of the top line with the bottom line, which are all left-handed, sit in an SU2 left doublet, and then all you're left with are the right-handed parts of the electron on top. But the generation is the index of 1, 2, 3. E1 is E, E2 is mu, E3 is tau. We'll see today that there's a little bit nuance because of the Yukawa term. This, what I just said, is a little bit oversimplified because of the Yukawa term. We'll talk about that. Well, maybe I shouldn't have made that comment, but anyway, we'll see. So there are 6 quarks. The quarks are top, strange, bottom, up, charm, and top. And they're organized again in 3 generations. These are going to transform to the left-handed side of the top and the left-hand side of the bottom are going to transform in an SU2 left doublet. The right-handed sides are going to be transforming as separate, right? So the notation was that there was EM that I was splitting to 1 Majorana, right? And then there was this other Majorana. And then, so, right, sometimes you write lepton, right? LM. Then for the quarks, yeah. So we had the, wait, actually, you know what? No, let me not say this because I'm gonna write down the projections as well. So we'll see. All right. So here at this point, this is what the particle description. These are what the leptons are, and then there are 6 quarks, right? I had on the next slide. So electron, there will be a left-handed piece and right-handed piece, but we're gonna split the electron into the PL epsilon plus PRE. These epsilon and E are the Majoranas for splitting them to, right? So the epsilon will be E left, epsilon E left star. And the right-handed guy is going to be minus epsilon ER star ER, right? Now this is an SU2 doublet in the following sense. PL of L is a lepton, PL of nu, PL of E. These are the left-handed guys. Good?
Sorry, just for clarity, those nu and epsilon are just Dirac experiments. Just when they're experimental.
These guys?
Yeah.
They're not. This is Majoranas.
Ah, yeah.
This is Majorana.
Yes.
Yeah. This is Dirac.
Yeah.
So the other guy to be added here is PR of E. Good. All right. Now the quarks, there are 3 generations of them. There's up and down, which is curly U, this is the guy who's left-handed is going to transform in a doublet. Right? Right-handed, down, left-handed, right-handed guys, and this is how they transform. So now I have to give you the charges, right? These are leptons. So this is what I was these are leptons, so they're transforming 1, 1. This is a left-handing doublet, right? The left-hand doublet, so it's 2, and this guy is right-handed, so it's 1. Minus half is the hypercharge of this guy, and this is minus 1. So the distinction between this and the Carl notation is that you don't have these PLs, PRs, right? It'll be a little bit simpler to write things out. Good? All right. Then the quarks, they're going to be the left-handed doublet, which looks like that, the left-handed part of this Majorana up, Majorana down. These guys are quarks, of course, so they transform as fundamentals, and then there's the right-hand part. They transform as fundamentals, so 3, 3, 3 under SU3 color. This is, of course, a SU2 doublet, and this is 1, 1, 6, 2/3, -3rd. So the convention is that, well, these are SU3 doublet representations, fundamental. I could, in principle, represent these using 3 vectors. Because of spontaneous symmetry breaking in the electroweak theory, the convention is that, at least in this course, when we write these vectors, we are representing SU2 doublets, right? We're making the SU2 representation theory manifest. Because it's more subtle, because of spontaneous symmetry breaking in Higgs, we have to keep track of that more. But in principle, you could pick SU3 and then you don't have to,
You said that the right-handed neutrinos transform as 1, 1, 1.
So right-handed neutrino does not exist. If it existed, it had to be 1, 1, 0.
Why is it?
0 is the charge of a U1. In representation theory of an abelian group, all representation of abelian group groups are one-dimensional. So if you want to label them, you label them by the charge. Right? So you put 0 because it has to be charge neutral. Good?
Here, why don't you have PR curly U or PR curly D in the
because that part is made up. So let me explain. So here's electron. And this was exactly the confusion I was trying to explain. So this is electron. Here's P left electron. Here is P right electron. Right? This is chiral mode. This is chiral mode. What am I doing? So this guy has only the top two components. I introduce a guy. So take the top two components of this and copy it in a matrix here, and then do my epsilon, this thing star, and this is my definition of D. Similarly, do this both sides. Copy it down here, right? And then put minus epsilon that thing star. And that's my definition. Oh, sorry. No, that's right. That's okay. So this is E. This is my definition. Right? When I'm describing the SU2, what's coupled to SU2, so then of course it's clear that PL of E is the same thing as PL of E. Right? Because I just copied this, the rest I made up. So that's why. So I could put the Diracs, but I'm keeping track of Majorana's. Right? Yeah, this Majorana business, you might find it confusing, but good. Now, again, to repeat, here, these are the hypercharges. It's not a dimensionality representation. It's an abelian group. U1 is an abelian group. It's all representations of abelian groups are one-dimensional. This is a charge. Good? This is exactly what I just said. So the left and right hand piece of Majorana fermions are complex conjugates of each other, right? With that epsilon thing. They're the charge conjugates of each other. And these are what these guys are. So you could have this. You could define these guys, right? And as a matter of fact, yeah, you got to keep track of them when you write down the gauge transformations and all of that. The charges are, you see, because they are the antiparticles, right? Their charges, this copying is making an identical antiparticle with it for it. So the charges of the antiparticles are going to be all the exact same charges with the hypercharge with a minus sign, right? The hypercharge has an extra minus sign. Well, sorry, no, these guys are going to be 3 bar. The quarks are going to be 3 bar.
Excuse me, sorry. So in the Majorana basis, you have particle antiparticle.
Mm-hmm.
What's happening here?
So that's what I'm saying. You start with a Dirac. You split it into top two elements and top 2 bottom. You could work with this, but I'm gonna tell you this. I'm saying that So this has 2 degrees of freedom. It's like, like think of 2 vectors, 1, 0, 0, 1. You could, after unitary, you could send this to 1, 1 and send this to 1 minus. Right? It's a choice of unitary. It's a little bit similar to that. What you're doing is that you had a while which had the top 2 guys or something and the bottom was 0. Now you rotate this to a basis where the top and the bottom are related by this relation. You just copy it, right? The rule says exactly how you copy it, right? And then this, the way it acts on the other guy is sends it to this one, okay, right? That's what it's a basis. It's a choice of basis. It's a basis. It's a choice of basis that diagonalizes the C operation. C operation wasn't diagonal, right? When C acted on psi Dirac, it gave you minus I gamma 0 gamma 2 psi transpose. That's why you gotta do these tricks. Not every book does this. As I said, like I think, well, Shrednicki doesn't do this. I think he sticks to chiral basis. Yeah.
This would be pretty convenient.
Let's say it again.
The neutrinos were actually higher on. This would be a very
I would still argue it's still a very convenient basis. I would argue. It's a matter of what you're comfortable with. I prefer this basis. But as I said, not everybody does. Like Shrednicki wrote his whole book in chiral. A lot of people use chiral. So the representations of the gauge bosons are pretty obvious, right? G mu alphas, these are the gluons. They transform under 810, right? They're the adjoint of SU3C charge. W mu A, they transform under 130, of course, and B mu is 110. All right. Now we also have a complex scalar field we call the Higgs boson, and it transforms in 1, 2 minus half. 2 means it's SU2 charged, it's SU2 left. Thanks God, that's important. Minus half is it has hypercharge. This 1 is means that you're not going to mix gluons with Higgs. What would have gone wrong if you were mixing gluons with Higgs?
They would have required mass.
Yeah, they would have required mass. That's bad. You would have broken SU3 as well. You don't want that. The thing as we go through spontaneous symmetry breaking, the thing that I want you to keep in mind is structure. Meaning that you basically have really one parameter, the VEV, vacuum expectation value of the Higgs, that sets everything. All the masses, everything is coming through this. So maybe in the lecture that we're going to talk about beyond Sanoma, I'll comment on this. I think it will be the next lecture. Every time there's a reason that in condensed matter people don't write scalar field theories. They start with fermions. They start with gauge bosons and fermions. The whole course might have given you the impression that, oh, scalar field theory in the infrared is the most natural thing. Well, we saw that there are issues with scalar field theory, and we're going to see the most important thing is mass. Mass is not protected, it's going to grow, right? So scalar field theory, we're going to talk to that. This is phenomenologically a little bit icky. So Sanomoil minimizes his use of scalar field theory, and it's all in Higgs, and that Higgs is already philosophically problematic, not at the level of quantum field theory. It involves some fine-tuning. The thing that you need to know about this is that when we were teaching quantum, when we were teaching KFT1, and we went through representation theory of particles, at that point, maybe you had less motivation to put a lot of focus and thought on spin zero. Sorry, zero mass representations. We saw that zero mass representations are special. right? For example, for a vector field, the number of degrees of freedom was different, right? Photon cannot acquire a mass. Is the world, everything will go to hell if photon acquires a mass. Why? Because that means that there's a brand new degree of freedom. It has to come from somewhere. Quantum mechanics cannot introduce that, right? But scalar field theory, the number of degrees of freedom doesn't change between massless versus massive. Mass term is a little bit awful so it's good phenomenologically, but it's hard to motivate this from a UV perspective. We'll see that. You already know that because it's relevant. So all along, we always talked about, oh, irrelevant things are bad. Relevant is good. But now we're seeing that the relevant is not very good either. So marginally relevant is good. If it's very relevant, it will grow like crazy. And it means that you have to fine tune it to be very, very tiny at the cutoff scale so that in the infrared you get something decent. All right. So now what's the Lagrangian Rostano model? So let's start writing down the part of the Lagrangian that was already implied by representation theory. Here's the Yang-Mills part. Here's the Yang-Mills part for SU3, SU2 left, U1, Y. This part should be clear. Any questions about that? All right. Now, the left-handed leptons, here's the action for it. Majoranas, and this is the right-handed lepton Majoranas. Right? So there's the left-handed piece, which is 1, 2 minus half, and 1, 2 half, the right-handed piece. Right-handed leptons, there's these two pieces. If we use a while notation, then there won't be these two separate pieces. For quarks, we're gonna have the Q bar D slash Q, U bar D slash U, D bar D slash D. These two are SU2 doublets. These guys are singlets. Why is there only one of this and two of these? What happened to the other one? There are no right-handed neutrinos. This is the right-handed element of this. Electron had the right-handed part, but not the. All right. Okay, any questions about this part of the action? Now, what else can I add to this? Let's see my next slide. Okay, what else can I add? Oh, let's just ask. What else can I add to this action? Higgs. So you can add Higgs, right? Well, we're gonna add Higgs, but just did this matter content? What can I add? I can add. So in every, sorry, one more thing to say. These have, each of them come with a coupling. G1, G2, G3, right? You could put it this way, in the definition of F mu nu, or you could take this out and put it as 1 over G squared outside. Maybe I wasn't very explicit about this, but I've been using this notation going back and forth a million times, right? But you also can have this term, F tilde F. This was something that in the abelian case was E dot B. We're going to see that this term will violate a discrete symmetry, CP. This term, or time reversal, will be violated due to this term. In principle, if you have a gauge theory, you should consider such couplings, theta. So far, there are these, but this is gauge invariant, right? G1, G2, G3, theta 1, theta 2, theta 3. These are the couplings that we have.
Did you include the ghosts in the Yang-Mills spot? I mean, they're implicit there.
It's a classical Lagrangian, right? I'm not writing the video for powerful Lagrangian. Classical Lagrangian. So I haven't decided quite yet. It's classical Lagrangian, right? I haven't told you I might be doing tree-level diagrams. I might want to do loops. Once you start doing those things, then you do Fediev-Popov.
So the second term also, you said that it violates the
CP.
I mean, it also violates the E going to B, B going to minus C.
The duality.
Yeah. So is it?
That
is the U1 case.
Yeah, that's related to that. Indeed. I'm going to comment on that next time. But I want to say one more thing. This term is topological. It doesn't change the equations of motion. Something I did not include in the homework. I should have. It's easy to see. It does not change the equations of motion, adding this term. So what does it do, actually? So classically, why would you ever add such a term? What's the consequence of adding such a term? No, but what's the consequence? If I'm saying it's topological, it does not change the equations of motion. What can it change? The only thing it can change is that if you have a boundary, right, you're going to pick a boundary. Equations of motion are going to be unchanged. When you use equations of motion, it's up to boundary terms. But let's say I don't have a boundary. Then what? Why would I care about this? Okay, I have not explained this. There's a beautiful story. In quantum theory, it matters. It shifts the energies. That's just for you to think about. Classically, it really doesn't play a role. So I also said that the fermions must be massless earlier, but now let's see how it works. If there was a mass term for fermions, it would break the gauge invariance. Take the right-handed part of electron or any of the electrons. No, tau muon. What is a mass term? It's this guy multiplied by its bar. I can put PL plus PR in the middle. Each PR, I can write that PR squared, right? So I can take the PR term and write it this way. The other one, I can write PL. Now, what is this? The hypercharge of this is -1, if you remember. What is the hypercharge of this guy? This is conjugate to PLE, which is hypercharge -1. So this thing has hypercharge -2. So if it will break, including a mass term for fermions, will break the U1 hypercharge gauge symmetry, because this is not gauge invariant. It has charge, right? Is that clear? So all fermions that we're going to include are massless. We don't see massless fermions around, so it better be that they acquire mass through spontaneous symmetry breaking. All right, good. Now, before I show you spontaneous symmetry breaking, how it works, I want you to deduce it a little bit. So when we did spontaneous symmetry breaking in the abelian Higgs model, we had a mu, right? And we had some scalar field phi, right? How did phi end up giving mass to mu? Giving mass to mu means changing the propagator, right? How did it happen? Do you recall what the mass term looked like?
Your expectation value.
Right. So exactly. So this was V plus something that was fluctuating, phi or whatever. There were these V's that squared of them sitting next to 2A mu's that gave you a mass term up to some constants. To arrange for such a thing, you should have some sort of a vertex that mixes these two guys to start with, right? If Higgs is to give a mass to something, you better couple to it, right? So if Higgs is going to give mass, what is Higgs going to give mass to? It's going to give mass to our gauge bosons, right? So some of our gauge bosons. So it's going to couple to the W mu A's, and then what else? B mu, right? Is that implied? Do you see a coupling already there? Yeah, because I said it has charge 2 under under SU2 left. So that term is in there, is the covariant derivative is there. But then if it wants to give mass to fermions, how is it going to give mass to fermions? You have to couple it to fermions. So you need a term in the Lagrangian that has a scalar and then fermions in it. Have you seen such a term? Yukawa, exactly. So let's write the Yukawa term. What is Yukawa term? It has to be Lorentz invariant. So there's a scalar. What should I put here? Made out of spinors to get something. Yeah, so it has to be first a bilinear fermions, and the charges should cancel. Right? So we need Yukawa terms to give mass to the fermions. All right, we're gonna get there. So now let's start with the Higgs. Higgs is SU2 singlet. All the fermions are either singlets SU2 or doublets in SU2 left. Higgs is a doublet in SU2 left, right? 5 plus 5, 0. Sometimes I talk about epsilon phi star, which is this phi tilde, which is 1, 2 minus a half. What is that? It's the anti-particle of the Higgs. It's a complex conjugate, right? All right, here are the Yukawa. So here's the Higgs. Here's the Higgs action. So this is the covariant derivative of the Higgs that takes care of this and this. That takes care of the coupling of these guys. It will give mass to the gauge bosons of SU2. There's V of phi, spontaneous symmetry breaking to Renshaw. This was our favorite action. Now, each of these terms are Yukawa terms. For every fermion you want it to be massive, you better put the Yukawa term. So here's phi. You want to give a mass to LMs. So phi is an SU2. So let me actually go through this. Phi is an SU2 doublet. So this is a vector. Here, one of the fermions can be an SU2 doublet. The other guy cannot be. And that one that's a doublet has to be conjugate. Right? So that's the reason behind this form. So you put phi, which is SU2 doublet, next to LM bar, so that is a transpose and give you SU2 neutral. And then you have to put something else that I'm going to put PR of EN. So M and N are generation labels. They're not diagonal. Right? So what I'm writing looks like this. So I could write down something like this. I could write down phi E, which is E1 PR. Actually, yeah, so this phi is my notation 5 plus phi 0. Now, what is this guy? This guy is gonna be up to gammas, is gonna be neutrino 1, right? And then the other one is, well, P left, neutrino 1, P left, neutrino, electron 1, iron. It looks like this. So these guys are going to contract together. And this is the guy that has to be SU2 neutral. This is a term that I'm giving a coefficient F11.
Sorry, why does that guy in the middle have? I mean,
because can you have a term like this? No. Why? It's a spinner. You want a term in Lagrangian, which is Lorentz invariant. This is Yukawa. It's Yukawa. It's bilinear inside. That's why we started with this. Now, the point to notice here is that I'm allowing these guys to be non-diagonal degeneration, right? So the right-handed electron will have a term will have a Lagrangian, a term in the Lagrangian. That's a Yukawa of the Higgs. Right-handed electron, and then left-handed tau or something, right? Tau and neutrino. So it's not diagonal. That Fn is important. Fmn is important. It's not diagonal. So this will give mass to these leptons. We're gonna do a similar thing with quarks, right? And then these and U's, there will be separate terms for these and U's. Here, we only had the right-handed electrons because there were no right-handed neutrinos. So there are 3 sets of these guys, and the Hermitian conjugate is Hermitian conjugate, right? So we have 3 3 by 3 matrices worth of couplings, Yukawa couplings, right? 27 Yukawa couplings at the moment. Naively. Okay, let's stare at this and see if you understand the notation. This is very important.
So why the middle term is not PLEN? Why is it?
Sorry, middle term, which middle term? This?
Similar. Yeah.
Oh, this guy.
Yeah.
Why is it not what?
PL.
So, first of all, PL of what? EN. So that, yeah. This is made up, remember? This is what we made up. The actual matter content was the left movers and right movers, right? There is no such a thing. Or another way of saying is that every time in the Lagrangian you write things, if you write something like this, it better be SU2 charged. Or another way of saying is that if you view these guys, yeah, I mean, that's in the Hermitian conjugate. Yeah. Any other questions? That was a good question. This Isha Mahana will come back on. Yeah. So let's do a count. How many couplings do we have? Let's start here. Well, here, how many couplings do we have? Three, right? How many? We said there are three more here potentially, right? Theta 1, theta 2, theta 3. So those are new parameters. 6. Now, there are no mass terms for fermions. Now, what do we have here? We have one parameter lambda here. We have mu, another parameter, right? We have 27 parameters here. Seems like it. Oh, so far. So, but I'm overcounting. This is not the number of parameters. All right. But this is all based on what you know, right? It's all the numbers are growing because there are 3 generations, right? Okay. Yeah, that's it. Let me pause here and let's reflect, take a moment for this to sink in. This is the Lagrangian span model. That's it. This model explains everything you want to know. It's a Lagrangian, you're going to quantize this, and that will be our best understanding of nature from a fraction of a second since the Big Bang until now. Good? Questions about this? It's a good moment to ask. It's not that complicated if you think about it, right? It's not that complicated. If the claim is that it's explaining everything, we had no mass terms for electrons. Everything is coming through spontaneous symmetry rectangle.
So when you see this gigantic equation that doesn't fit in our model, it's just basically expanding all over there.
Yeah, they're writing the electron and neutrino and tau. They're cheating. Yeah, of course. Yeah. It's not that complicated. Well, the complicated part is in this piece actually. So I'm going to use terminology. This is flavor non-diagonal. It's flavor changing physics, right? Flavor changing physics. All right, so let's talk about the spectrum of this theory. Still classical. By that, what do I mean? I mean spontaneous symmetry breaking. What do? We give a vev to the Higgs, and I'm going to pick a unitary gauge because let's kill degrees of freedom. Gauge degrees of freedom. Let's keep track of physical things. I don't want to keep track of extra junk. We can't afford it. So the good thing about the unitary gauge is that it gets rid of this gamma A vertex mixing thing. And if you wish, in the unitary gauge is arc C gauge in the limit of C going to infinity, right? That's what it was. All right. So Higgs is, so first component, I'm going to give it to 0 in this notation I'm using, right? Fixed component, I'm going to give it to 0, say to 0. And then the second one is 1 over square root of 2 V plus H of X. H is what's called Higgs. H is actually the, well, no, H is the scalar that fluctuates, right? And then this is the VEV. V is the minimum of the potential. V squared is equal to mu squared over lambda. That's the minimum of the classical potential, right? All right. So to get our hands dirty, it's a little bit nuanced. So I will try to slow down a little bit. You see it once. If you keep track of a bunch of terms, you can understand what's going on, but it's good to get it right first time. So because everything comes out of the Higgs field, let's explicitly write down the covariant derivative of the Higgs. Oh, I erased it. This is what's going to give the mass to the gauge fields. What is it? It's 1 over square root 2, 0 del mu of H minus I over 2 square root 2, 0 V plus A, nu plus H, V plus H. This is my gauge content. Let's stare at this. Do you recognize this? Should I write on the board?
Pauli's though.
Yeah. So what this is G2 TA W A sum over A mu phi. Yeah. Good. Oh, sorry. No. The covariant derivative also has the B mu G3 in it.
U1.
Mu, oh, sorry, G1. Right? So this is a nice notation because you could just view this as an identity, put it in SU2, right, and write it down.
That looks like taking the generators of U2.
Yes, that's exactly what you're taking. So it looks like U2. But it doesn't matter, it's the degrees of freedom, yeah, right? In U2, U1 of it decouples, right? Okay, so SU2 left times U1 hypercharge, 2 minus 1. 2 is the structure of the W mu's, and minus a half will tell you what? Yeah, this is all in this, capture in this business. Good? Everybody's good with me? All right, so let's take the kinetic term, which is the covariant squared. Let me zoom out so you can see all terms. There will be a term coming from here, minus a half. Now you see why I put square root 2. Minus a half del mu H del mu H. That's the kinetic term for the fluctuation of Higgs. There will be a term that is minus 8 V plus H, which is coming from here, right? Then W mu1 minus I, well, okay, so this term, I factored G2 out, right? This term, this guy with the same copy on the, and with this guy and the same copy. There is this term, and then there is this. So if you take d mu of phi and put it on the other side, what do you have? You have two matrices, two of these matrices being multiplied. There's this guy, and then this guy dagger on the other side. This is what it looks like. Now let's go through this term by term. This is the kinetic piece of the Higgs. This V, there's a power of 2. This guy squared will give mass to these guys. But notice what it looks like. It looks like it's giving the same mass to W1 and W2. Right? If you expand this, it's giving the same mass to W1 and W2, and it's V2. That's the first prediction of the Sano model. The masses of W1 and W2 better be the same. If they are the same mass, it's convenient to just package them in these linear combinations. We're gonna call this W plus and this is W minus. Keep that in mind. Now let's look at this. This is Higgs. This sitting next to this tells you that Higgs is, this term is going to give you coupling of Higgs to W plus and minus. Right? W1 and 2 are going to couple this. Good. So we got out of this a mass term for W1 and W2, same mass term. And then a coupling between Higgs and W1 and W2. But the point is that the couplings are all related. The couplings and masses and all of these are related. Again, we start with a bunch of parameters. Everything is decided by these parameters. Oops. Now, this term V squared will give mass to, look at this combination. Will give, now this is important. It will give mass to what? Can you stare at this and tell me?
No.
This is tricky. We're gonna, it is a little bit tricky. We're gonna expand this. It will give mass to a particular combination of W3 and B. And the other combination remains massless. You could expand this and see it. It's just algebra, a bunch of terms, but I'm going to do it for you. But I'm warning you in advance what's going to happen. All right? That's one thing. So one of them will get mass, and then there will be coupling of Higgs to W3 and B mu. So maybe this is misleading for combination. Okay. Now we also have the Higgs potential. We got to expand. So this is the Higgs potential expanded. We get a mass term for the Higgs itself, which is not what we start with, right? And then there will be a Higgs self-interaction, H cube and H4. Let me help you see what these terms are doing. So from the top, what we got is that we got mass terms, but then there's this W plus, W minus. Well, actually, if this is Higgs, do you see this vertex from the first line? So W plus, W minus are W1 mu minus I W2. Right? So this comes from the term which is diagonal here, 2VH that. It changes W plus to W minus. Right? We also have this term. Right? That's the H squared term. Good. The rest of it I will not analyze. The line below I will not analyze for now. That will be the next slide. But the Higgs, you see there is a mass term for Higgs. This vertex. And then there's this vertex. Good. All right. There are also Yukawa couplings. So let's see how the Yukawa couplings give mass. This is what a particular term was, right? This was the FMN terms, right? So what does it look like? It looks like WM bar transpose EM. So these are P left, sorry. PL. So what does this look like? So this is 0 V plus H. It becomes V plus H PL E bar PR EN, right? So there will be a vertex between Higgs and the two fermions. That's still a Yukawa term. But then the V will give a mass to these guys. Have you noticed something interesting here? The mass is not flavor diagonal. Right? The mass is not flavor diagonal because these are N and M. Good. Do you have a suggestion? What do we do? Last time we found something that was the mass was not diagonal. The mass, there was a mass matrix. What did we do? you usually diagonalize it and write the other terms as off diagonal. You don't like off diagonal mass terms, right? That's what we're gonna do, and that's actually what's gonna cut down on the number of parameters. Well, my counting was silly to start with. Those parameters were not all random. Okay. So we're gonna diagonalize the basis of the leptons that we wrote down, so that we're gonna be talking about the mass eigenenergies, right? Eigenstates. Good. This slide is pretty dense, right? You see what's going on. I think most of the slides are dense, but usually I go through them fast. All right. It's QFT2, so all right, so here's the case of the this is bad. I'm missing PLs all over the place. Good. By the same philosophy. Oh, I forgot to say this. Nobody asked. Look at this. Do you notice something different here? Yeah, but what's tilde? Antiparticle Higgs. You put that there as well for a reason. Can you tell what the reason is? Or what the consequence is? So the consequence is that previously we had 0 V plus H. Now we have V plus H up here. It's basically what we want to pick up mass. So this is the combination you end up with, and you get mass for the your quarks. All right. So putting all of this together, this action I was trying to construct here looks like this. There is the kinetic term for Higgs. There is the mass term for Higgs, H cube, H4, right? Then there's V plus H. This hopefully you know what it is. This W plus W minus, right? This notation is a little bit too quick. Then the rest of it I repackage as minus I minus G2 W mu 3 plus G1 B mu 2. This guy is also picking up. I'll do this on the next slide. Maybe I should have delayed this for a bit. And then these are the what do you call the terms turn into? All right, now we're gonna go through this. So what's the spectrum? At the end of the day, we're organizing the spectrum in terms of the EREFs of Poincare. So it will be labeled by spin and mass. So what are the spin 0 particles that we have? We have a Higgs. What's this mass? 2 lambda V squared equal to 2 V squared. That's the mass. What are the spin 1 particles we have? We start with the WA bosons and the B mu, but then we ended up with this mass term. They both got the same masses, G squared 2, V2 over 4, right? And now there's something funny going on. So what actually set the masses to be equal? Do you know what it is? What it is that Higgs did not completely break the whole gauge group. There's some residual gauge symmetry. There's a gauge transformation that turns the W mu to the W1 to W2. Let's see that. Take the W's are charged under what? What are the W's are charged under SU2 left times U1 hypercharge, right? So this is all I have to decide to talk about gauge transformations. I'm gonna pick them to be independent of position. So these are just numbers. I'm gonna pick omega 2, omega 1, and omega 2 of this 2 means SU2 left to be 0, and omega this means the U1, right? And this is the third component of SU2 to be equal. This is a gauge transformation. What does this gauge transformation do? I claim they send W1 to W2. Can you see it? I don't expect you to see it. That's why I include a slide to go through this. So here's a gauge transformation of W2. Good. It's minus del mu of omega 2a minus epsilon ABC. These are the structure constant, W2 of B of X, W mu C. First, I took this gauge transformation to be independent of position. That means this term goes away. So you have this. Now I have three of such guys. I picked the first and the second to be 0, and I only kept the third. Here's the third, and this is the third. When I put the third here, this is A and C. This is the antisymmetric tensor, right? Which means that the variation of delta W2 is minus W1. Why? Because that is 1, 3 was here, 2. 1, 3, 2, that's plus. No, sorry. No. That is, A is this one. 2, 3, 1, right? So it's plus, so it's minus. And then this guy will be this. Does it now look like a transformation that rotates them to each other? No, it's just a unitary that rotates them. This residual gauge transformation is the reason they have to get the same mass. Right? It makes no sense if they had different masses, because the gauge transformation will convert them to each other. Now, what is this unbroken transformation? It's a U1 of electromagnetism. It's when U1 is omega 1 is equal to the third component of the SU2 left. So the charge associated with this is T3 plus hypercharge. T3 is the third component of the generator of the third component of SU2. So Pauli Z.
Why is that called isospin?
Apologies. I'm sorry. I did not make the choice. I didn't make the choice. That's what it is.
Doesn't it come from the
Yeah. But I mean, where did that come from? Chicken and egg. So as I said, it's convenient to define W plus W minus so that your mass term looks like this. But the piece, there is one more gauge boson that you're left with. So these are your gauge bosons. There is the gauge boson, which is minus G1B mu plus G2 mu 3. This acquires a mass. You normalize it this way. So it's convenient. Remember that G1 and G2 are not couplings of SU2 left and SU2 right. So we're going to mix them in the following way. You define a single parameter out of them, which is G2 over square root G1 2 plus G2 2, which is this W of theta. And I can talk about the sign of it, which you know what it is, right? G1 G2 2. So we're going to parameterize things using, for example, G2 and delta. Now, Z boson is this guy, and it acquires the following mass. W boson, W plus and minus, they have this mass. This has this mass, right? This is the mass of the other guy, and this is the mass of these guys. One mode remains massless. This is the mode. This is the orthogonal mode. Stare at it. W3 cosine theta minus B mu sine theta. This is W3 sine theta plus B mu cosine theta. This is it's explicitly written. This is the massless gauge field that survives. It's the U1 of electromagnetism. This charge is T3 plus Y. Good. So this is a photon. So we broke it down. We got Z got a different mass. W1 and W2 got the same mass but different from Z. There's one massless mode, which is the photon. So in summary, here's what it looks like. What do we have in terms of our spin 1 particles, right? Spin 0, we just had Higgs. Spin 1, we have W plus W minus. Z, they have their own masses. They have a massless mode, mu, and we have 8 gluons. We didn't give a color charge to Higgs, therefore the gluons remain massless and they're good. Like it. All right, so these are all their gauge spin 1 particles. What about the spin half? So the spin half particles get masses from the Yukawa. Now, as I hinted at, it's convenient to just diagonalize these guys to start. But remember, what is the cost of this? It means that when you wrote your initial Lagrangian and you call something electron, that was an actual electron. Because if the electron is something that has a fixed mass, as in the low energy that's coming out of after spontaneous symmetry breaking, this is not that thing that you wrote initially in the Lagrangian. That was some other field. And this is a linear combination of those guys. There's some field redefinition, right? All right, so you diagonalize this. There's F, E, F, U, F mu, F tau. Similarly, GMHN, FMs. Right? Now, after diagonalization, this is your Yukawa. These are Yukawa terms, masses that we obtain, right? FMV becomes the mass of this guy, EM, whatever it may be, U and D, and so on and so forth. We're going to go through this next time again in a little bit more detail. I'm running out of time. All right, maybe I should pause. Questions here. Notice that, so here we had 5 bar for G, Mn. Sorry, this is the antiparticle phase. This is the very first time in this course that we're talking about something like precisely phenomenological, right? Like a particular model of coefficients. So all along, it's been about build a theory. All right. Okay, so now let's talk a little bit about, I think I have a couple more. Yeah, talk a little bit about hadrons. So this was all about the electroweak business. What about the QCD part? What about the gluons? So G3, remember that this is a non-abelian gauge theory, the fate of which is going to be decided in the infrared by its coupling growing. At around 500 MeV, this coupling becomes so strong that the theory confines. Remember I told you about dimensional transmutation? This is the scale. Let's introduce quantum mechanics, and nobody can derive this from first principles. What is the consequence of this? The consequence is that quarks and gluons are no longer in the spectrum. The spectrum, the theory confines, everything must be color singlet. So what are the possibilities of color singlets? We're going to give them names. You could have a bound state of only gluons. Right? That makes sense? What are the gluons? They all come with a label alpha, which is representation theory of TA, of SU3. It's possible that you could construct some, putting a bunch of them together and get something that's SU3 invariant. Such things are called glue balls. Of course, they won't be like that. The theory is strongly coupled. It's not a free theory to put the representation together. Right? The theory is strongly coupled. Deep in the infrared, these are emergent degrees of freedom. It's not correct to think of these as a bunch of gluons. Like it's not, you can't say 4 gluons or 5 gluons. It's just a glue ball. Right? That's the best terminology.
Have we observed those? Are those observable? Yes.
It's just next to you.
It's actually fairly recent.
But they, I mean, given that, do they have this?
Yeah. It's a balanced state mass, right? Like if you look at the proton, most of the mass is not the quarks.
I'm so glad someone else is here.
Yeah, so there's been like people we thought were in blue balls, right? The firms we thought were blue balls, but only until recently.
All right. Then we have mesons. All along, the example that I wanted to give you, but I couldn't, saying that there are emergent particles in the infrared is mesons. QCD, deep in the UV, is a bunch of gluons and a bunch of like quarks. But in the infrared, these particles is what we see. They are to be understood as bound states of a quark and antiquark. Right? They're bound states, so they have a lot of binding energy. Then you have U D bar as a first example of this. It's called pi plus. You have du bar, it's called pi minus. You have this funny combination, uu bar minus dd bar, square root 2, which is pi 0. So these are some of the mesons, but we have a lot of particles in QCD.
You understand that as the tensor product of an up quark and a down antiquark?
All right. There's no tensor product here, first of all. So these are fields, right? And the fact that we say it's UD bar is to be understood. It's a bound state of a strongly coupled theory, right? So this has been deduced from sort of like gradually go to higher and higher energies and try to deduce what's in there, right? That's what's in it, but it's full of gluons in a sense, sticking them together, right? There's no tensor product here.
So if I want to create, if I go to canonical quantization, I have my quark field, and I want to create a particle. I take the creation operator in the vacuum. I create the particle.
So remember one of the very important things that I said about strongly coupled theory is that there are the UV particles that you thought you were describing, and then there are emergent particles. And it's futile to try to describe the UV things as in terms of ANA dagger of infrared things in terms of ANA dagger of the UV, unless it's a very, very particularly simple theory, right? If we could do that, then we would understand QCD. We can't do that, right? There's no simple way of describing this. This part of it is completely phenomenological, if you wish. Well, we have lattice models, so we can run things on lattice and see these things happen. But there's nobody sitting there just doing, I'm not going to give you a homework problem to derive the mass of these guys. Good?
Good.
This is a problem that people in the 70s thought it was the problem of their generation. It still continues with the problem. We made a lot of progress on other stuff, but QCD remains very, very difficult. All right, then we have, very importantly, bound state of 3 or more quarks. For the 3 quarks, well, these are called baryons. The names are important, right? Mesons, baryons. You need to know what this means. Glue ball, mesons, and baryons. The world is made out of them. Baryons, up, up, down is a proton. Up, down, down is a neutron. Now, is there a process that turns a proton into a neutron? Yes. It plays a very, very important role in physics. What would that process, what should it involve staring at this? It would have to involve a U and a D and something else. Right? So it will have to be a vertex with U and D and something else. But this is, yeah. Good? Yeah.
Do you know for like the quark states, like when you have like four quarks, like what's the difference between you having four quarks and two mesons?
Well, it's really a question of it's a question of bound states.
Exactly. Yeah.
And that's precisely the question you're asking is that what's the difference between 2 particles and a bound state of the 2? So the 2 particle, it's all about the following. Like when you have 2 particles, you have 2 bags of 2. Like there's a mass here, there's a mass here, and then you bring them closer and closer. They have potential. As long as the potential is negligible compared to the mass of the 2, that we still think of as 2 individual particles. As soon as they come so close that the interaction potential, the interaction part of the energy is comparable to their masses, this is sort of the starting point of quantum field theory in QFT1. there's no sense in which you could say they are separate particles. This is when their individual wavelength, the Broglie wavelength, become comparable to like their interaction. Well, they cannot separate. Yeah. There are that's actually a very, very good question. Okay. Anyway.
And okay, are we going to look at the residual strong interaction?
Sorry?
The residual strong interaction.
Residual strong
The part that keeps protons and neutrons together.
keeps what?
Protons and neutrons together.
Oh, what holds protons and neutrons together?
No, but not they mass bound states, but within the neutrons.
Oh, yeah. There's a lot of this is the start of nuclear physics. There's like a subfield of physics called nuclear physics that takes this and runs with it, right? So they just hand the portion nuclear physicists, and I claim no knowledge. I don't know anything about this past this point. So, all right, so we gotta wrap this up. I think. Oh God, I have a couple more slides. Do we have like 5 minutes? I'll go through this so that next time we'll start fresh. It's actually I'm going to tell you a little bit about terminology that I'm going to use next time. We're going to talk about charged current interactions and neutral current interactions, and Kobayashi Maskawa matrix K. Kibibo. I'm missing Kibibo. He would be upset. All right. Anyway, but the thing to remember is here's the Higgs coupling. Here's the Higgs gauge boson coupling, right? This is the Higgs fermion coupling. 9 Dirac fermions, 3 Majoranas, neutrinos, and then they remain massless. The neutrinos remain massless. They remain massless because there's no right-handed neutrino to write a Yukawa term to start with. Right? Now, here's the important point that I didn't want to skip until for next time. A consequence of spontaneous symmetry that I've been saying it over and over again. This is a huge success of Standard Model. All particles coupled to Higgs with a coupling that's proportional to their mass. Right? Because they get the mass through interaction with the Higgs. It means that Higgs, well, the Standard Model particle physics is telling you about this relationship between the mass of all these particles. They have to be all set by the interactions, right? So that's something interesting. And the coupling to Higgs is M over V. V is the VEV of Higgs, which is 246 GeV. 246 GeV. Remember that? 500 MeV for QCD being strong. Electroweak spontaneous symmetry rate. Electroweak symmetry rating is way larger, higher in energies, right? 246 GeV versus 500 MeV.
How was it measured? How was that expectation value measured?
Oh my God. Okay, that's the mass of Higgs. When Higgs particle was discovered, that was what made the world go crazy, right? Now, the point I have here is that M over V, because V is so gigantic, M over V is small for almost all particles, which means that almost all particles are weakly coupled to Higgs, which means that it could use perturbation theory. That's good. Except for one beast, the top quark. The top quark happens to have a mass which is 173 GeV. By the way, these numbers I'm quoting, I don't tell you what scale, blah, 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 who cares, right? This is just, you know that I should code the scale, scheme, all of that. 173 GeV, which is pretty darn close. So the top quark physics is not perturbative. Perturbation theory is going to struggle. Another thing that I said already is that Higgs fermion interactions are flavor changing. Right? And after we diagonalize things, the only flavor changing interactions are W plus minus. I have one more thing to say, which is Higgs couplings are CP symmetric, strong interactions. These theta terms are the only CP violating terms. I'll talk about this next week. Blah blah blah. This is my summary. I'll skip that. I just want to flash this. All mass come from the Higgs. So the mass of a particle is this coupling to Higgs times the Vev of Higgs. Thank you. Any questions?
But that most of the mass in the universe comes from conformal anomaly.
Okay, what?
Like this doesn't like 99%
Oops, sorry.
of the mass in the universe comes from conformal scale anomaly or conformal.
No. There's a lot of problems. I have a lot of problems with what you're saying.